Okay, so we're still working through some examples with integration by parts. And here is an example where it may not appear that integration by parts is actually the technique you want to use, but it turns out that it's actually very helpful. So if you think about it for a second, this integral is not something that we know how to do yet. Don't rush this one and look at that and say, oh, that's just 1 over x. It's not. That's the derivative of the natural log function, not the antiderivative. So what should we do here? Well, we're going to attempt integration by parts, and this is a cool technique that works when you kind of don't know what else to do with an integrand. I'm going to let u be the entire integrand, natural log of x, which means dv is just the differential part of that, the dx. Okay? And we're just going to see what happens. So if I take the derivative of u and get du, I'm going to get 1 over x dx, or, you can also write that this way, dx over x, that's the same thing. If dv is equal to dx, that would mean v is just x. Okay? So now let's set up integration by parts. The integral of the natural log of x dx is equal to what? Integration by parts says that I multiply u times v, which is going to look like x natural log of x. Okay, minus the integral of v du. So that's going to be x times dx over x, v du. But what happens here? Those x's cancel each other out and leaves me with just an integral of dx. Well, the integral of dx is just x, so I get minus x as my answer. And notice that one was actually pretty quick. Once again, please do this on your own. I highly encourage you to check this to make sure that this works, that we didn't make a mistake somewhere. And remember, the way that you check is you take the derivative of your result and see that the answer to that is the natural log of x. You get your original integrand after differentiating this. Okay? So that's a good thing to remember. Integration by parts can sometimes help when you're integrating a function that doesn't necessarily look like a product of two things. It still can be the technique to go to. Let's try another one. This is an interesting function. Okay? I want to evaluate the integral of e to the x cosine of x dx. Now this may look kind of similar to our first couple of examples because there's an exponential function which we've seen, and there's a trig function which we've seen. But those first couple of examples that we did, one of the two functions was a polynomial. And I had said before, it's best to choose that polynomial to be the u and let the other thing be the dv, because then that power on that polynomial will shrink down, which is ultimately kind of what we want to have happen. There's no polynomials here, so how do we choose u and how do we choose dv? Well, we're just going to go with a hunch. I'm going to say let's let u equal e to the x, and let's let dv equal cosine of x dx. So this would mean that du is also e to the x with a dx attached. This v here would be sine of x, is the antiderivative of cosine. Now that I've worked all this stuff out, let's set up our integration by parts. I have the integral of e to the x cosine of x dx equals uv, so that's e to the x times sine of x, okay, minus the integral of v du. So this is going to look like e to the x sine of x dx. All right. Remember, the goal with integration by parts is to try and get an integral here that's simpler or more manageable than the integral over here. And so far, this seems to be just as difficult as the one that I started with. So I'm not sure that that's going to be something that I can just evaluate right away. But we have also seen that sometimes you need to apply integration by parts more than once. So maybe that's what we need to do. Let's try this again with another application of integration by parts. I'm going to kind of go with the same strategy as before. Let's let the exponential function be u, and this time dv is going to look like sine of x dx. So once again, du will equal e to the x dx. V in this case will look like negative cosine of x. And now I can work this out with integration by parts. So this is going to be equal to e to the x sine of x minus, remember, put square brackets here. It's easy to forget to do that, okay? Inside the square brackets, I'll have uv, which looks like negative e to the x cosine of x, negative e to the x cosine of x, minus the integral of v du. So if I look at that, v du, I have a negative here, which I can bring out to change that to a positive. Now that that negative's gone, all I'm left with is e to the x cosine of x dx. Okay, so let's see what happens here. All of the work that I've done has shown me that my integral of e to the x cosine of x dx is equal to what? E to the x sine of x. Let's distribute that minus sign into my square brackets now, plus e to the x cosine of x. That minus will change that plus back to a minus again, so now I have minus the integral of e to the x cosine of x dx. Now you might be looking at that and thinking, shoot, like I've done integration by parts, and this integral over here, which I'm kind of expecting to make things easier, has gotten me right back to where I started from. This is the integral that we started from in the first place. So does that mean that we've hit a dead end? Actually, no. This is a good thing that this happened, because what I'm going to do is take this equation now and think of these two integrals as like terms, because they are the same integral. That means I can add this integral to both sides to cancel it from that side, giving me 2 times the integral of e to the x cosine of x dx equals, I'm going to simplify what's left on this side. I'm just going to call that e to the x times sine of x plus cosine of x. Now, if I divide both sides by 2, I get that the integral of e to the x cosine of x dx is equal to 1/2 e to the x times sine of x plus cosine of x. And check it out. I have the integral that I started with equals an expression, and there's no integrals left to evaluate in that expression. That must mean that I have a solution now. So that's a kind of a clever technique, using integration by parts until this integral matches the one that I started with, and then I can treat them like terms and combine them and solve and so on. So that worked pretty well. Let's do another example. This is the first example that we're going to do in this section where we have a definite integral instead of an indefinite integral. So for this guy, we are looking at the definite integral from 1 to root 3 of arctan of 1 over x. Okay, once again, this doesn't actually look like a product of two functions. In fact, your first gut instinct might be to say, let's use u substitution, because I have a composite function, arctan of 1 over x. Oftentimes, u substitutions are helpful with composite functions. We tend to let u be the thing on the inside here. But you're going to find that if you do that, it doesn't make this any easier. So we're not going to try a direct u substitution. Instead, let's try what we did when we had the natural log function. And let's let u be the entire integrand, arctan of 1 over x, in which case dv will just be the dx here. V would then be x, but what is du? So this is a tad tricky because it's a more complicated derivative to evaluate to find du, but it's doable. So if it was arctan of x, the arctangent of x it has a derivative of 1 over 1 plus x squared. But instead of x being squared, I have this inside function here. So I actually need to apply the chain rule. The chain rule would say that I have 1 over 1 plus this thing squared, 1 plus, and if I think of this as x to the negative 1 power, squaring that is actually going to give me x to the negative 2 power. So that's kind of a simpler way to think of that. But then because it's the chain rule, I also have to multiply by the derivative of this inside function here. So if that's x to the negative 1 power, its derivative would be negative x to the negative 2 power. Okay? You go ahead and verify that that's correct. That's a good little bit of practice with derivatives. Okay? So now that we've gotten all this, I can't forget to put my dx there. Let's include that. Let's set up our integration by parts. So I have the integral from 1 to root 3 of arctan of 1 over x dx is equal to what? uv, which looks like x arctan of 1 over x. Now, because this is a definite integral, I don't want to just leave this expression by itself. We have to evaluate it from 1 to root 3. So definite integrals are going to have this additional little thing here for your uv term, because we're going to evaluate that in the next step. Okay, but let's see, what else do we need? Minus the integral of v du. What do I get if I multiply v and du? Well, I have x times this expression. That x gets multiplied up into this numerator, and that will add 1 to that exponent, giving me x to the negative 1 power there. Let's take the negative from my du and bring it out also, so I can make that a positive. Over 1 plus x to the negative 2 power. Okay? Now, looking at this, you might be thinking that that definitely looks a lot different than the integral that I started with. Am I able to solve this using any techniques that I already know? And yes, we can. It's going to help to simplify it a little bit. I don't like dealing with these negative powers right here, so I'd like to eliminate them both. You can do that by multiplying this by x squared over x squared. And then let's put our dx term right there. Okay? What's that going to look like? Well, let's come back here. Let's evaluate this. So this is going to be x, which is root 3 times arctan of 1 over root 3, which, if you prefer, is the same thing as root 3 over 3. That's if you want to rationalize the denominator. That's a little bit more familiar when we're trying to figure out what this arctangent is, because I recognize that from my unit circle. Minus 1 times arctangent of 1 over 1. So that's arctangent of just 1. So notice I'm just evaluating this expression here and here as we do with definite integrals. What happens to this guy? Oh, and I almost forgot to include my limits of integration. Let's make sure those show up too. Plus the integral from 1 to root 3, x squared times x to the negative 1 power is just x over 1. Actually, no, it's not a 1. This x squared distributes and makes that an x squared instead of a 1. But this x to the negative 2 times that x to the positive 2, that part does become a 1. Okay? And now the expression that I have, x over x squared plus 1, is doable with a u substitution. Here, I'm going to let u equal x squared plus 1, so that du equals 2x dx, and I have an x dx in that expression. The 2 I can manage by multiplying both sides by 1/2. Okay? So let's see what this does. Root 3 times the arctangent of root 3 over 3. You should hopefully know your unit circle pretty well. That's going to give me the square root of 3 times, that's pi over 6. Arctangent of 1 is pi over 4. Okay? And then here, when I do my u substitution, what do we get? I get plus. So for a u substitution, there's a couple of things that need to change. First of all, my integrand needs to be put in terms of u, and my limits of integration also need to change into u values instead of x values. So my integral, when I take that 1 and plug it in here, 1 squared plus 1 is 2. I have a 2 here now. And then root 3 squared is just 3, plus 1 is 4. Those are my new limits of integration. And then I have x dx, which is going to change into 1/2 du. But let me bring the 1/2 out. And then I'm also going to have u in the denominator here. So this whole thing just becomes du over u, which is a familiar integral. Okay? Okay, let's write this as root 3 times pi over 6 minus pi over 4 plus 1/2. This, when I integrate, is just the natural log of u evaluated from 2 to 4. Now what do we have here? Root 3 pi over 6 minus pi over 4 plus 1/2 times the natural log of 4 minus the natural log of 2. And then I'm going to use a logarithm property to combine these two things, because I know that natural log of 4 minus the natural log of 2 is the same thing as the natural log of 4 divided by 2, which is just 2. So putting that all together, I get root 3 pi over 6 minus pi over 4 plus 1/2 natural log of 2. That's going to be my final answer. You may look at this too and think, oh, I have another logarithm property. I can take that 1/2 and make it the exponent of this 2 and call that the natural log of root 2. I don't really consider that to be any simpler than this, so I'm going to go ahead and leave that in that form. Okay? We have a couple more examples to do. Let's do that in part 3.